So in the last session, we've been talking about the rank and basis of a finitely generated free abelian groups. And we found that the number of elements in any basis that generates a free abelian group is a constant, and that is what the rank is. Now let us take a much closer look at the free abelian groups, finitely generated free abelian groups. So the first thing what we are going to establish is a necessary and sufficient condition for a set of elements in a group to be a basis for that abelian group. So the necessary and sufficient condition is like this. Let S be a subset of an abelian group G. Then the following conditions are equivalent. The first condition is every element of G can be uniquely expressed as G equal to n1x1 plus n2x2 plus dash 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 plus nr xr, where xi's are in S and ni's are integers. That is the first condition. The second condition is G is generated by S, or S generates G, and n1x1 plus dash dash plus nxr is equal to 0 implies ni is equal to 0 for all 1 less than or equal to I less than or equal to. So this guarantees a necessary and sufficient condition for S to be a basis for an abelian group G. If this condition is satisfied and if S generates G, then S is the basis. So we have two parts to prove here. One implies 2 and 2 implies 1. So 1 implies 2 involves proof of two statements. G is generated by S, and if this is true, all ni's are zeros. But the first part is very clear because it clearly says that every element of G can be uniquely expressed as this. So it's clear that G is generated by S. But we still have to prove that if this is true, then all ni's are 0. The first claim what we are going to do is 0 does not belong to S because let X belongs to S and X is equal to 0, then Y belongs to S can be written as Y and Y plus 0, which actually contradicts this statement uniquely expressed as. So Y is not uniquely expressed and hence 0 does not belong to S. Now let us assume this is true. N1, let n1x1 plus dash dash plus nrxr equal to 0 and nj is not equal to 0 for some j. If all nj's are 0, there is nothing to prove. So we'll assume that one of these, at least one of them is not equal to 0. So this implies that xj is equal to xj plus n1x1 plus dash dash nrxr, because this is 0 and that is equal to, there is an nj here which is not equal to 0, so this can be written as 1 plus nj xj plus n1x1 plus dash dash nj minus 1 xj minus 1 plus j plus 1 xj plus 1 plus dash dash nrxr equal to 0. nrxr, because this is already 0. This plus this is 0. So we are expressing xj two ways. So xj is equal to xj and xj is equal to this form 1 plus nj xj plus this n1x1 plus dash dash nrxr. That means xj is expressed in multiple ways. So this is not uniquely expressed. xj is not uniquely expressed, and that implies all ni's are 0. Two implies 1. See, X is generated by S means that every element of G is generated by S means every element of G is expressed as a linear combination of elements from S. So it is actually generating it, but we need to still find out it is uniquely expressed. So it's clear that every element of G can be expressed as G is equal to n1r1 n1x1 plus dash dash nrxr. So let us assume that G can also be expressed as G is equal to n1 dash x1 plus dash dash nr dash xr. So this implies n1 minus n1 dash x1 plus dash dash nr minus nr dash xr is equal to 0. If this is equal to 0, the second condition says that the coefficients of each of these xi's are zeros. So this implies ni minus ni prime is equal to 0 for all I, and that implies ni is equal to ni prime, and that means G is uniquely expressed as n1 x1 plus dash dash nr x. Now let us find out a different way of expressing a basis from existing basis. Meaning, suppose you know the basis of a finitely generated free groups. Can we find another set of bases, another set of elements that forms a basis for this group? And that's what we are going to find out. So the result is like this. Let S is equal to x1 dash dash xr be a basis for an Abelian group. If it's a basis for an Abelian group, that means this is a free group. Then for an integer t different from 0, the set S prime x1 comma dash dash xi minus 1, ith element is replaced by xi plus t xj for some other j from the set S, comma xi plus 1 comma dash dash xr is also a basis for G. See, the number of elements in S and S primes are same. The only thing is the xith element is replaced with this. So there are two parts to prove. One is G is generated by S prime. If S generates G, G is generated by S prime also. The only difference between these two is that we don't have an xi in this. So if you find a way of recovering xi from the elements of S prime, then we are done. Meaning we need to find out xi in terms of elements from here, and that is equal to xi plus txj minus txj. So this is an element here. This is a t is different from 0. So xj is an element from here. So we are trying to find out, we found xi in terms of elements from here as a linear combination of elements from here. Implies S prime generates G. But that does not mean that this is a basis. It generates G, but does not mean that it is a basis for G. In order to prove that this is a basis for G, we need to find out it is linearly independent. Meaning, if n1 x1 plus dash dash n I x plus t xj plus dash dash nr xr equal to 0 should imply that all ni's are zeros. Okay, so this means that n1 x1 plus dash dash dash, this is xi. We'll take the elements of xj out. So this is ni xi plus dash dash plus ni plus t or nj t of xj plus dash dash nr xr is equal to 0. We are actually reordering this. But x1 x2 dash dash xr is a basis. That means since S is a basis for G, n1 equal to 0, n1 equal to n2 equal to dash dash ni plus njt dash dash equal to nr equal to 0. In between you have nj also equal to 0. So this means ni plus njt is equal to 0. And that means nj is already 0, so that means ni is equal to 0. And that means if this is 0, all the coefficients of the elements from S prime are zeros. And that implies S prime is a basis for. Let us take an example here. Let us say let G is equal to, this is finitely generated free Abelian group. So one of the bases S is equal to 0, 1, or let us say 1, 0, 0, 1, because every element of this can be expressed as a linear combination of this. So with this, what this mean is S prime is equal to 1 comma 1 or 1 comma even 2 comma 0 comma 1 is also a basis. Now let us take a look at the finitely generated Abelian groups in a different way, a different notation. So let us start with a definition. So let G be an Abelian group, and H1 and H2 are subgroups of G, such that the intersection of these two groups is the set of, or the subgroup of just the identity element. And G is equal to H1 plus H2. When I say H1 plus H2, this means that H1 plus H2 where H1 belongs to H1 and H2 belongs to H2. Then G is the direct sum of H1 and H2 and is written as G is equal to H1 plus H2 with a circle here. Or you can say H1 I from 1 to 2. If you take an example, let's say G is equal to Z. It's a plane. It's a two-dimensional plane. And this is our H1 and this is our H2. So that means H1 is H1 is generated by 1 0 and H2 is generated by 0 1. This is actually equal to N0, N belongs to C. This will be 0 N, N belongs to C. So what happens here? H1 plus H2 are actually M comma N, M, N belongs to C. What are they? They are actually, these are elements of H1 and these are elements of H2. So the elements of G are the sum of these points, that is actually this. So all integral points, and that is exactly what G or Z cross Z is. Z cross Z means this is actually equal to Mn, M comma N belongs to C, and that is what we have here. So G is actually Z cross C is equal to H1 H2. Okay, so this is actually nothing but a different way of expressing the direct product of Z and Z. See, H1 is isomorphic to Z. H2 is isomorphic to Z. So G is equal to Z cross Z and G is also equal to H1 direct sum H2. A different way of expressing the direct products. This can be extended to any finite number of finitely generated Abelian groups. So that means the direct product of finite number of finitely generated Abelian group is same as its direct sums. See here, instead of saying H1, you can say Z. And instead of Z, you can say H1 because they are isomorphic. So you can say same as sums of the isomorphic group of the groups involved in direct products. So this is a different way of looking at the direct products. And one more thing I want to see here is, let us say G is a finitely generated free abelian groups and it is expressed as a direct sum of two different or finite number of subgroups. So let us say I is equal to 1 to n. This is actually similar to pi I is equal to 1 to n Zi. Sorry. Because these are all finite number of elements. This is a direct sum of finite number of subgroups. This is actually direct product of n finitely generated groups. Now, the rank of G is equal to the sum of the ranks of HIs. Once you are expressed, once a finitely generated free group is expressed as a direct sum, the rank of this is the sum of the ranks of this. Because if you take any two of the participating groups here, its intersection is 0. So it is uniquely expressed as elements from Xi's. So there is no common elements in the base. So the rank of G is the sum of the ranks of HI.